Hi guys, this is Kevin Wynn and Isaiah Boone, and today we are going to talk to you about the fundamental theorem of line integrals. Okay, so before we can talk about the fundamental theorem of line integrals, we need to talk about the fundamental theorem of calculus. So this theorem states that for a continuous function t on the interval from a to b, the integral of the function on the interval is the difference of the antiderivative of at b and the antiderivative of a. So as you can see, it's this equation right here. Okay, so what I actually meant to say that it was for a continuous function f, not t. It's been corrected on the screen, so yeah. So, after looking at that, it turns out that there's a similar concept that can be applied to line integrals as well. Okay, so for the fundamental theorem of line integrals,
In multivariable calculus, one of the things we have wanted to calculate has been the work done on a particle by different forces. The specific problem we are trying to solve here is the work done by a force field F on a particle as it moves along a curve C. We found that one method of calculating the amount of work done was by parameterizing the curve, but it turns out there is a theorem similar in format to the fundamental theorem of calculus that solves this problem. The theorem The theorem states, supposing f is a gradient vector field that is continuous along some open region containing the curve C, letting f be the potential function for the gradient vector field f, and letting a and b be the starting and end points of the curve C, the work can be calculated along C depending only on the start and end points. And this is equivalent to f of b minus f of a.
so a key aspect of the fundamental theorem of line integrals is that it works with conservative vector fields. And so the fundamental theorem of line integrals states that the work done by a conservative vector field is the difference in the two endpoints such that the work done by any curve between the endpoints is equal.
So here we've explained the proof of the fundamental theorem of line integrals. It's actually pretty straightforward, and we've skipped a couple of steps just to show the simplified version. But so basically what we're doing is our function f is the gradient vector function of f of x and y. And the curve that we have here is defined by r of t, which has the x component x of t and the y component y of t for t between a and b. And we have that a is equal to r of a and big B is equal to r of b. And here what we're doing is we're letting g, this new function that we're creating being equal to f of r of t. And so that we see here when we take the derivative of g with respect to t, we get the product of the derivative of f of r of t and the derivative of r. And this is just because of the chain rule, which is something that we learned early on in calculus. So we have two vectors here. The first vector has the derivative of f of r of t with respect to x as this first component, and the second component being the derivative of f of r of t with respect to y. And then as our second vector, we have dx as the first component and dy as the second component. And this can be simplified to the gradient vector function of r of t times the derivative of r with respect to t times d of t. And as you can see when we used it earlier, this is the equivalent of work done on a curve C by a force field F. And by substituting back in what we have for g of t, we see that the fundamental theorem of calculus can actually be applied. And the work done on the interval from a to b of the integral of the derivative of g is equal to g of big B minus g of big A, which proves our theorem to be true. So we actually have an example problem here where we're trying to calculate the work done by a vector field with a first component equal to 5y plus 5 and a y component equal to 5x on the line moving a particle from 0, 4 to 5, 0. And so in order to do this problem, the first thing that we have to do is make sure that there actually is a potential function. And the way to go about doing this is through a symmetry check. And in order to do a symmetry check, you take the second derivative of the vector field you have there, and this gets you a 2 by 2 matrix for a two variable vector field and a 3 by 3 matrix for a three variable vector field. But in this case, our vector field or the derivative of our vector field gives us a matrix with the components 5, 0, 0, 5. And as we can see, this matrix is symmetric, and we therefore know that it has a potential function. And through just a few more simple steps, we see that the potential function is equal to 5xy plus 5x. And as we showed earlier, using the fundamental theorem of calculus, all we need to do in order to solve this, the rest of this problem, is to plug in our two endpoints. And so what we do is we plug in our b point, which is 5, 0, into the equation, and then we plug in our a point, which is 0, 4, into the equation. And by plugging them in, we're able to find out the work done by subtracting the two. And you can see here that our result is 5 minus 0, and that's equal to 5.
So the reason why this works for work is because given a starting point, which can be seen as your initial potential energy, by releasing that energy into kinetic energy, we reach a new endpoint such that the kinetic energy is equal to the difference between the potential energy at those 2 points. So yeah, and now you know the fundamental theorem of line integrals and why it's important. All right, thanks.